Ladies and gentlemen, welcome to one more of the Epic Online Technology Meetings today. Today we talk about PIC testing. And let's do something together. Let's address the elephant in the room. So when it comes to understanding the success of photonic integrated circuits, what's the elephant in the room? While many are talking about PIC packaging, whether it's onboard optics, pluggable chips, chip bonding, or the need to control the temperature, we are still, to some extent, ignoring testing. And that's because testing is very difficult to do. And if things don't work, it is always somebody else's fault. On Monday, November 16, we are organizing an online technology meeting to address PIC testing by answering a different question. Rather than arguing who has to test what, I believe we should be making a clear definition of what is testing. Many companies are interested in what needs to be tested so they can automate the process, which explains why EPIC members like ficonTEC, IMEC, and Tegema, who make the manufacturing equipment, are working with other EPIC members like Keysight or Quantify Photonics, who make the instruments. In my preferred future, we would have a PIC testing machine. You could present it with a PIC wafer, and the machine will compare it with a reference and give an instant answer, yes or no. Integrated photonics for datacom is very clear. A chip has to meet the so-called Telcordia standards. In other applications like LiDAR or biosensing, there are no standards. In this very special Epic Online meeting, we are discussing the application independent and dependent testing demands. I want to understand more than just reliability or lifetime, but for example, what kind of vibration can the system withstand? So let's bring the PIC supply chain together to address this elephant in the room with PIC foundries, equipment manufacturers, photonic characterization specialists, testing houses, and last but not least, the end users. So see you on November 16th at 3 p.m. Central European Time to test how we can build business opportunities while removing the biggest hurdle in PIC industrialization. 1, 2, 3, 1, 2, 3. This is Mission Control in Nordbike. 1, 2, 3. Testing. Can you hear me? Ladies and gentlemen, it is time to start. It is time to find cooperations. I must say that the business of PIC testing is not new for EPIC. Many of you actually went 2 years ago to a beautiful city with a tilted tower. You went with me in Pisa and we actually got the ball rolling there. We managed to bring all the companies who wanted to offer testing ideas to companies who make equipment and have foundries using the whole thing. Already for 2.5 to almost 3 years, Ignazio Piacentini from ficonTEC, it was his idea. He's the one who contacted EPIC and said, I have something in mind, let's try to work together, let's meet in Pisa. We did that 3 years after. We have a lot of success stories to tell, but also still a lot of challenges. First of all, let's start. Thank you. I still cannot believe it. You know that already for 3 weeks we are the largest photonic association in the world on behalf of the whole EPIC. Thank you so much for making this happen. I still can't believe it. For those of you who don't have much plans from now till Christmas, today we have PIC testing. Every Monday and Wednesday we have online technology meetings. So mark your calendar at 3 o'clock. We have, for example, 3D sensing next week. We have photonics for pharma in 2 weeks. We have LiDAR for factory automation. Pay attention to that one. The agenda is fascinating. Medical devices, naval and aeronautic, and just before Christmas, food and beverage, because we all deserve great Christmas this year. And also I would like to say that EPIC keeps growing. We have already 14 people. We're hiring more. We are actually looking for more talent. EPIC is really flourishing these days. Thank you so much, because without you, I couldn't be able to do this. My team and me, we are very happy to organize events. We're very happy to connect every company with anybody, keep giving us challenges. We are helping companies raising capital without a commission. So if you are looking forward to raise some money for your company, contact us. We also have the biggest website in photonics to find a job. Really, www.jobsinphotonics.com. That's today the largest website to find a job in photonics. And all of you know this, but I will just repeat, because you're an EPIC member, you have a long list of market reports. All of them, they are available for you to use and abuse. And also Today we talk about PIC testing. First of all, I would like to acknowledge our media partner, Fibre Systems, for being publishing and publicating and making promotion of all the event, but also, most important, because without you, this couldn't be possible, I would like to acknowledge sponsors. Deep breath. We start with Finland, we start with Modulight, all the way from Finland, Tampere, this company does MBE growth and all the way to packaging and manufacturing of semiconductor lasers. So we go to Valencia, go to VLC Photonics. They're in the news now because they were recently acquired by Hitachi. So congratulations to my friends from Valencia. Let's have some black rice. But VLC Photonics is the one-stop shop to offer you service over the entire supply chain. Design, they have great design services. Testing, you're going to hear that about that later. And also they have their own IP building blocks to access the foundries. Tegema, Eindhoven, these guys rock. Tegema offers packaging and testing equipment based on active alignment. Long tradition in the semicon industry. Now they are here to offer you the entry point for PIC testing and packaging. We go now to Jena, the capital of optics in Europe, and we talk about Jenoptik. All of you know Jenoptik because of these optical instruments. But what you don't know is that Jenoptik supports the PIC ecosystem in various ways, from testing of optoelectronic modules with their probe, you're going to hear about that later, to also integrating into different applications with the track record micro-optics. And if we want to talk about the supply chain, we have to talk about ficonTEC from Aachen next to Bremen in Germany. ficonTEC is that company who offers the machines that are revolutionizing the packaging and testing of optoelectronic devices based on active alignment. These guys have managed to automate everything that has to do with the packaging and testing of photonic integrated circuits. Congratulations to ficonTEC. Newcomers, Photonics 42, all the way from Milano, from Italy. Photonics 42 is a new company offering services, packaging and testing services with track record from companies like Cordon and ficonTEC. These guys have managed to make a service one-stop shop to test and to package your chips. Welcome to the community, and thank you very much for all of you to listen to me. And also, I would like to acknowledge and thank my partner in crime and very good friend all the way from Barcelona, Dr. Ana Gonzalez. What's in the menu today?
Hello, everyone. Thank you, Jose, for this kind introduction. We have an exciting meeting coming up this afternoon to talk about needs of PIC testing. This is a very interesting field to explore, as it's a key process in any related PIC-based product. So yes, this is our agenda. The main speakers today are foundries, companies doing automation, and companies providing testing services. So yes, these talks are going to be very interesting, but they are going to be used to trigger discussions between the entire supply chain attending this event today. So yes, we have the companies developing PICs, also testing solutions. We have all the foundries. We have companies doing optical network equipment, the lasers, optics, micro-optics, material, wafers, coating. So well, yes, the entire supply chain here to discuss about the challenges in PIC testing. Yes, well, just to finalize, I would like to highlight the pilot lines in photonics that are represented here today. So we have a fabulous for free-form micro-optics for going to large volumes. Also, we have the JPICS pilot line for indium phosphide chips, pilot production, and pre-commercial and commercial production of indium phosphide chips. Also, we have a MIRFAB for prototyping and also for going to large volumes of chemical sensors, miniaturized chemical sensors based on mid-infrared technology. And finally, PICSAP, the packaging pilot line, for packaging and assembly, also for testing. So yes, back to you, Jose.
Ana is that person who has spent the last 4 years of her life promoting pilot manufacturing in Europe. She is our pilot lady. Congratulations, Ana, on the amazing job that you have done bringing pilot production to Europe thanks to European Commission funding. This slide represents only the companies who have registered for this meeting. So if you are missing the logo of your company, it's not our fault. Register to the online technology meetings and you will be there. And now let's say hello to the YouTubers in the world. Hello, YouTubers, how are you doing? In the next 2 hours of your life, we are going to connect you with potential partners, suppliers, and customers. If you want to get in touch with any of the participants today, all you have to do is send me an email, jose.pozo@epic-assault.com, and I will make that introduction. jose.pozo@epic-assault.com. I love introducing companies. Also, please feel free to post your questions in the YouTube chat. This is also valid for the people in the Zoom room. If you want to get in touch with each other, just use a private chat and get in touch with each other. After the meeting, we have one-on-one meetings. So for those of you who didn't have enough after 2 hours, you can stay, and my colleague Helena Jelinkova will introduce you and will set up a private Zoom room for you to do business, because this is what it's all about, cooperations. And when it comes to cooperation, the supply chain, there is nobody better than our first speaker today, the person that got this activity at EPIC, personal friend of mine, caro Ignazio Piacentini. Thank you very much for being with us this beautiful afternoon. Let's address the elephant in the room. The
Good
attention of
afternoon,
everyone
Jose.
goes to you.
Thank you, Jose. Thank you for the introduction. And let me share my screen. Can you all see me? Can you all see my screen? So good afternoon and good morning for those that are from overseas. I have 6 minutes, so I will fly through my few slides, and my intention is not to present specific products, but to stimulate question and answers in the audience. So the title is really, what are the requirements for PIC wafer level testing? And I refer to wafer level testing because if we solve that, we also solve chip testing and device testing. So let's get started. So I have 6 minutes. So as Jose was saying, we started quite a while ago. So we started in Pisa in 2017, February, and there is one graph that we've been showing over and over again, showing that one of the costs in the production of PICs is testing. So really follow me to these slides, and let's make this as interactive as possible. So testing is not new at EPIC and is not new at ficonTEC. And for those that have not noticed, including my friends at EPIC, my title has formally changed as from the 1st of April. So I'm no longer the Director of Business Development, though I still do a fair amount of that, but I'm really the principal of photonics testing in ficonTEC. So I would like to clarify, first of all, what is a characterization and volume production testing. There is one slide from Professor Meloni from 2017, which I'm not going to comment, but simply put, characterization, you verify, validate, measure whatever you like, whatever you can in the time that you need. Once you go to volume production testing, you really try to shed as much of that and simplify the testing to a go-no-go type of testing as cheap as possible and as fast as possible. And of course, photonics is fairly recent compared to semicon, but for guys like me that have been around for a while, there is a lot to be learned from semicon, from the semiconductor testing. Also quite few things that do not quite match. So if you look at semicon, you have stuff like JTAG, boundary scan, TAP, and it all began in 1985. So it has been around for quite a while and turned into proper standards. In semiconductor, you only deal with contacting electrical pads, however small, while you need higher resolutions, higher accuracy for optical probing. Combining optical probing, both vertical grating couplers, but also edge coupling, which is one of the trends where I believe photonics is going, and then add the DC and low frequency and even more radio frequency in the tens of gigahertz, then we'll put together a nice package of challenges. And photonics, whether we like it or not, is still very young, and maybe we've done more in packaging, but certainly not enough in testing. So, and here I raise a long list of questions. It's not an exhaustive list. It's just to trigger some response. So, do we need to test all the PICs on a wafer? Do we have to test simultaneous PICs to gain speed? Do we have to go from simple devices like VCSEL, 2 pins of a device emitting light, to complete transceiver photonics integrated circuits? Do we have to learn from LIV to bit error rate testing and eye diagram, the one I show on my slide? And do we always need RF? RF is more complex than optical. Can we bypass RF by having fallback using optical in, optical out only? Do we need extended temperature ranges? What do we do with all the data we collect? Can we use them for some statistics? Can we add artificial intelligence and so forth? How do we map it back to the production volumes? How do we map the results back to the wafer production and the KPIs, and how fast we need to go. Well, the list gets very long, and hopefully we will then try to address it. So I've been already mentioning the major ingredients: positioners and handling, probe heads, and the instrumentation. Of course, positioners and handling for a company like ficonTEC that produce mechanics is the easy task. Probe heads have to become specialized probe heads, maybe combining both optical and electrical, and the instrumentation is certainly another big task. So I see that time is going, so you will have the copy of this slide. You can always get back to me. So let's move on. So ficonTEC is better known for PIC assembly, but over the last few years, we've been doing more and more on testing and basically being dragged in by our own customers and by the market. I will not comment on these nice pictures, but we've been working on it ever since I started discussing with Jose. So instrumentation is a big chunk of it, and because it tends to be pretty costly. So if you want to go and test a large volume, you need a dedicated front end. You want to reduce the amount of different instruments you have hanging around. If you want to go faster, you need to test multiple channels with the mixed signals, electrical, RF, optical. So I would say that if you take this into consideration, then we need to trigger a better response from the instrumentation vendors. You see a few logos on my screen, and we really need to have a kind of mix and match modular instrumentation format. PXI has been around for quite a while. It was new when I was working at National Instruments in Austin, Texas, but we don't have anything better than PXI for the time being. We'll see what happens. The discussion certainly needs to be continued. And this is my conclusive slide. And so first of all, I hope that these fast 6 minutes have raised some questions, tickled some interest. There is a need to discuss more and harmonize and clarify what wafer level testing means for the community. And I would like to finish my short speech with an invitation, as I've done in other associations in my younger days. Can we envisage creating a specific task group which will really discuss and send out some clarified requirements for testing? And with this, I finished, and thank you for listening to me.
Okay, thank you very much, Ignazio. Super interesting presentation. Maybe you can come back before I stop sharing your screen. Can you come back to, okay, now you stopped sharing your screen. Well, it doesn't matter because I have the question. So what about your question about, do you think you have to test each PIC in the wafer? What do you think about this?
What I can answer is that most of the customers I've been discussing with, they do want to test every single chip. Now, from experience, I know that the distribution of yield tends to be worse on the edges of the wafer than in the middle. So I guess the need to test everything is also related to the specific device, how complex device, and what are the yields. And certainly, there will be cases where you might want not to test all the chips. And so while on a semiconductor, you can test all the chips or large chunks of the chips simultaneously, this is still pretty hard to achieve in photonics. I would like not to answer myself, but this is a very interesting question, and I would bounce it back to the audience and to the end users.
Yes, let's see about, because we have end users. In this case, we have all the foundries here in the room. So, for example, Milan from Cornerstone. Hello, Milan. Are you here? But you are mute. You are here, but mute.
Sorry about that. Can you hear me now?
Yes. What do you think about if it's necessary to test all the PICs in one wafer?
I think it's a really difficult question, and as Ignazio said, maybe we can have like a specific group talking about this. When we discuss with everyone, everything will depend, I think, on a specific market application and a target product, because you can see that silicon photonics and photonics in general expanded beyond telecom and datacom applications. So we are now targeting more and more applications. So definitely we will need, I think, not only to talk about testing, but also we will need a unifying material platform that can address a lot of applications and also reduce time to market and reduce the costs of the production. The built-in self-tests, I think, are very important, and definitely when we talk with many collaborators from the industry and from academia, everyone is saying that we need to have a target plan for testing. So we need to know which devices we want to test, what are the testing protocols, and according to some discussions, probably we need to set full automation and some built-in self-test in the future we need to have. But of course, everything will depend, I think, on a specific application. Ideally, it would be great to test every chip. But again, if we have like 8-inch wafers, there are typically 40 or 20 chips on the wafer. What are we going to test? Are we going to test every device, or just the device that is not really tolerant to fabrication uncertainties? Because we all know that wafer thickness varies about 0.24 nanometers, that ring resonators, for example, vary in terms of target resonant wavelength peak position, again, very, very much. So again, we need to discuss what specific device we are going to test and how we're going to do this. So I think it's a huge discussion about that. And as Ignazio said, maybe it's good to have a target group on, just working on this.
When I see my friend Milan, I get too excited. I have two questions for Ignazio. Sorry to jump in like this. I cannot wait. I have two questions for Ignazio. The first one is very, very difficult question. What is your secret? These pictures are from PISA, and you can see that you look exactly the same. It's 3 years of hard work, and you look the same in shape. Thank you for that amazing meeting that we had. The second question is a lot easier. For doing the wafer level testing, we need a probe. We need a electro-optical photonics probe. We need to probe every part of the wafer. What is the supply chain looking like these days in providing such probe? Is there enough technology for ficonTEC to integrate those probes into your machines?
Thank you, Jose. This is a very good question, and I didn't want to expand too much in my slides, but there are not that many companies worldwide that produce probe cards, and I am lucky enough to have probably the second biggest in the world, quite near home, close to Milan. The name is Technoprobe. They're not the only one. I believe we have two issues here. One is that photonics is still small in terms of volume. So you can imagine the 5G revolution, for instance, what it generates in terms of semicon, and this company, they serve very large customers. But certainly we do need combined optical and electrical probing. I am actually working on a couple of specific projects with some NDAs going, but I'm hoping to announce in early next year, possibly January, February, the first probe heads which combine both electrical and multiple optical. There are several ways of doing it, and we will probably hear from other companies today also different approaches. And I would say that what makes it difficult is also the large differences between different devices. You remember a few months ago, we were talking about VCSELs, a quarter of a million VCSELs on a 6-inch wafer, and then you have maybe 2,000 photonics chips on an 8-inch wafer. So those will require complete different approaches. But between the two extremes, we can also share something. Photonics 42, the new company you mentioned, together with the Polytechnic of Milan, is actually going to do some early test, because you can imagine if you put a multi-channel probe in your test chain, you have to validate every single fiber optics and every single signal path all the way to the instrumentation. So there are really complex things. It's not only positioning, it's data acquisition, which was one of my younger days, sort of a specialties when I was at National Instruments, and also, what you do with all your data.
There's a couple of companies have been discussing a lot lately about the probe cards. Tobias from Jenoptik, the capital of optics in Europe. Tobias, what are your views and what is your line of interest towards developing a probe card?
Yeah, first of all, I totally agree with the most points Ignazio said. So we are really try to give an answer on some of those questions. And one is the, maybe I can show some slide or one slide.
Yes, go ahead, sure.
So that's our UFO probe, we call it. That's an optoelectronic probe card, especially used to be used in existing standard prober equipment, and so that you can use your existing infrastructure. And it's a monolithically probe card which implements optical and electrical probes in a single probe card. And that makes it, you can use it like an electrical probe card in the same way of handling. And if you go even on a parallel way of testing, you can test several chips or dies in parallel. And since you use it on standard prober equipment, it's possible with certain improvement that the same personnel can test it. And we implemented in the market, and here are actual measurement values from production runs, wafer maps, and yeah. So the questions you always ask is what can an optic do for you? So we can really help the companies to drive their PIC volume test roadmap in the way that they can have a volume test. So, and we are, for instance, cooperating here with RoodMicrotec, which is a test house, also a PIC member, to really have this possibility in the market. And what we are looking for is to have more PIC test applications and even beyond applications beyond PIC testing. So photonics.
Very good, Tobias. And when you are talking here about the parallel testing, how many chips you can test in parallel?
That really depends on the infrastructure you have, because parallel testing means more optical measurement equipment, more lasers, more detectors, and so on. In principle, so we currently are able to cover an area of 150 millimeter in diameter. So and the number of optical in and outputs, it's in principle not limited, but you have to somehow get it into fibers to connect it with your equipment.
Okay, thank you very much. Okay, so now maybe we have a question from Wilfried from RoodMicrotec. Do you want to make the question by yourself, Wilfried?
It's okay. Well, I just wondered, so semiconductor industry is doing a lot on with metrology. So the question is, what do we test? So if we want to measure the quality of a grating or waveguide, so the edge depths, the edge widths, performance, so there's a lot of, this is basically metrology. So the question is, if it's not an electro-optical device, I think we can handle a lot with advanced metrologies, and this is already in place at the big foundries. So the question is, when we use probe cards here, what do we want to test and how reliable, what could we test that is not covered by metrology? So this was my question, basically to the users of the PIC. So how much do they trust metrology? That's what it comes down to.
So Ignazio, I think this question is for you.
Yes, I can certainly address this question. Basically, when we talk about combined optical electrical testing or chips at wafer level, we are past metrology, I would say. We use metrology for your processes, but not after production. You are trying to test, first of all, let's again differentiate between characterization. You are validating your design, you are validating how well you baked your first wafers, and then you go into volume testing. So volume testing could be, for instance, on a transceiver, you might want to test insertion losses. Where do you lose optical power in your optical pigtailing? You might want to go as far as testing bit error rates across a full transceiver. So I would really say that this is behind metrology. Where it gets a bit confused is that you might want to add automated optical inspection after dicing. Typically, let's go to some simpler devices again, like VCSELs, which I was addressing a few months ago. In VCSELs, we are supplying equipment that does the optoelectrical testing, basically LIV, with the optical power meter and injecting currents on a full wafer. Then you dice it, and you have the same devices on a blue tape. Then you do an optical inspection. You might have debris due to the dicing. You might have defects which are purely visible in optical. And then you combine the data, and the third step is sorting. You might want to grade the devices. They're not faulty, but you have different category of quality, or you have failures. So that is the basic differences. I see metrology mostly on the processes for wafer production. So at least in my mind, it comes before on the quality of the foundries themselves. Does this answer to your question, Wilfried?
Yes, Ignazio, thank you. Yeah, so it's mostly when we have an electro-optical system like a Mach Zehnder or something like this, then there might be some more testing required. Of course, for lasers or any types of source, you need to test them electrically. That's clear. I was just wondering more for the classical PICs, like the waveguides and the grading couplers and stuff like this. So more the passive devices. So that question is, yeah. But you're right. So as soon as you combine electronics with these more metrology features, you have to do both. Yeah, both types of testing.
Yeah, I agree.
Thank you. Yeah.
You're welcome.
Okay, so thank you very much for all this discussion. Thank you very much, Ignazio. Great presentation. But well, we hope you are going to talk more during all the meeting. And also thank you very much for your proposal for creating this working group. We fully support that. And well, maybe we can have some kind of, you can put in the chat if you could be interested, or we can discuss it later at the end of the meeting. So yes, let's create some kind of working group to answer all these questions. Thank you. And now let's move to the next speaker. So let's go to Valencia. And the next speaker is Iñigo Artundo. Hello, Iñigo.
Hello. Hi, everyone.
CEO from VLC. So please, well, if you want to start, the floor is yours.
Yes. Let me share my presentation. Okay. Can you see it full screen now?
Now, yes, very well.
Okay, thank you. So, this is going to be very short as well. We only have 6 minutes, so I'll try to fly through the slides. So my name is Iñigo Artundo. I'm CEO of VLC Photonics. I'll be discussing about some of the challenges we have with customers when testing chips and wafers for photonic circuits. So, quick company introduction. We are a company based in Valencia, in Spain. And we have been working with photonic integration technology since almost 10 years now. So we have our offices and clean rooms here. We are now 18 people. We have been certified for quality recently this year. And our most recent news is that a couple of weeks ago, it was publicly announced that we have successfully been acquired by Hitachi High-Tech. So we are now part of the Hitachi group. So we have been very active working with customers and serving their needs in different markets, mostly communications and signal processing like LiDAR or quantum. But we have been also very active in smaller niche markets for PICs like sensing or biophotonics, medical instrumentation, things like that. So most of our customers are actually developing new products based on PICs. And that is a long way from the very early prototypes you have, from the first concept you have. While you do product development, you reach the engineering phases where you actually optimize your product and you move into volume, into the ramp up, right? This requires, well, this very much depends on the application in terms of times and volumes, and also requires something that people tend to underestimate, quite a significant investment. And this investment, it doesn't necessarily go into the design and fabrication of the chips, but mostly in the testing and packaging, as we will see. So regarding the different stages, most of the times when we engage with customers on the early phases, proof of concept, alpha, beta runs, that is mostly development. And this is where you define the specs of your chip. You do a lot of prototyping, you run many different parametric variations of your designs, you even do some fab process or module development. You require a lot of testing here to be able to test all these different design variations, all these different building block parametric variations, or even the process variations themselves. Once let's say the prototyping is finished and you move into the engineering, what is known as pilot production, what you do is you freeze your design from the functional point of view, and the main objective here is to validate wafers, so to have as many wafers as possible with high yield and low cost. And there is a lot of testing as well here. The testing is not so much on the functionality, but more on the yield optimization part. And obviously, when you go into production, control or general availability, and everything is frozen, layout and process, it's all about getting non-good wafers or non-good dies, in theory, with guarantees for your customers. So the requirements are very different at each stage. When you do prototyping, you usually do bare die characterization. So this is, as I said, mostly used for qualifications of tens of dies usually, in order to ensure that you actually meet your requirements. You work a lot with fab metrology, as Ignazio was mentioning before, and there is a lot of process control monitoring information. And here, what you really need to have is a very good understanding of photonic integration and the technology itself to do the root cause analysis of the failures, because there will be many when you are doing prototyping, and there will be many things you don't understand and you want to optimize. So this kind of know-how is absolutely critical. Once you move into higher volumes and you move into wafer level testing, this can be done to validate wafers during the engineering. And here we are talking about hundreds, maybe a few thousands of dies, in the order of a few tens of wafers, let's say, depending on the chip size and material platform, wafer size, etc. And here the idea is that you will be able to qualify the manufacturing process, ensuring that it delivers consistent quality. And obviously, when you move into production, when you have, obviously this depends on the application and market, but let's say tens to hundreds or even thousands of wafers. I don't think many photonic applications nowadays are running into these volumes. It's all about sample the ongoing quality. So we know that mostly this is done using vertical testing for silicon photonics, wafer level. There's a big challenge on how to move to edge coupling. There is also a lot of debate, as Ignazio well pointed out, in how to combine optical and electrical, maybe in the same probe, maybe in different probes, even the need to do RF probing as well in these cases. But one thing is clear, you really need to move to very high speed trace acquisition. So you need very high speed instrumentation. You need parallelism in order to cope with the big volumes, and eventually to enable scalability for many applications. And one thing that was mentioned before as well, it's critical to have capabilities on the software side. So be able to deal with all this big data and be able to process that, all the measurements, and extract the valuable information from the analytics of these. There is eventually also another testing that comes after packaging, let's say the assembly testing, which is usually done at the package or module level, kind of a component. And this is more traditional than what has been done in the telecom industry for many years. It's all the physical testing, environmental testing, certification. I think this is better understood nowadays, so there's not much need to discuss now. So at VLC Photonics, we have been doing that for many years. We have a couple of clean rooms where we have plenty of equipment, mostly for bare die testing and wafer level testing, both electrical and optical. Very flexible systems because we address customers with very different needs. So we are able to accommodate the setups and our capabilities depending on the requirements of the project. And we even have some basic assembly capabilities that in many cases simplify the testing. We can do all kinds of electrical screening, optical coupling, both vertical and side coupling, take all kinds of measurements. One very important thing is that we can do that for every wavelength range you can imagine, from near infrared to all the near infrared spectrum and mid infrared. We have all the instrumentation and the components required for that. We also do that under the 35 processes and calibrations from ISO 9001. And given our 10 years expertise on photonic integration, we tend to help also our customers in debugging the test results and see how to proceed to the next design iteration. So if you want more details on our specific equipments and capabilities, please contact us. So that's everything I wanted to mention in these 6 minutes. Thanks a lot.
Thank you very much. Muchísimas gracias, Iñigo, for this presentation and also for being one of the success stories of the PIC ecosystem. I remember 10 years ago when you guys started offering design service only, where it's a design house, and you realized that there was so much more that needs to be provided to customers, that it was beyond a design, it was functionality. The customers wanted functionality, so you built an entire company out of offering functionality, and the success story is that actually only a few days ago, we have a capital investment from Japan. Hitachi has acquired VLC Photonics, and I love because these are two EPIC members with the idea of working together and build a bigger, even bigger one-stop shop. This Hitachi by offering now integrated photonics from EPIC member VLC Photonics. Congratulations from my heart. This is fantastic news for the PIC ecosystem. Let's go down to business. PIC testing. I have to tell you one thing between us. I have no idea what is the difference between testing and characterization. I thought it was clear to me. It was clear to me in my head because I come from academia and I did a lot of characterization. But I did realize that the customers of the companies like VLC Photonics do not care if it's testing or characterization. They just want to know if it works, and if it doesn't, what do they have to do to make it work? How do you feel about this, and what is in your mind the difference between testing and characterization?
That is a really good question. Actually, many people do not understand the difference. It's not that there is a clear definition written in stone, right? But I think there are three different aspects to this. One thing is the pure measurement, right? So how to couple the light in and out, how to position your probes, and how to take the measurement. But then the measurement is not the only thing to consider here. There is a lot of analysis, there is a lot of processing and interpretation of what you are seeing out of the measurement, right? And then comes the characterization and testing. Our understanding here is that characterization refers more to the bare devices, like in these cases, chips, dies, or wafers, while testing for us is more when you move into a packaged device or component, where you are also, because traditionally in the industry, testing also refers to, for example, environmental testing. It refers to, I don't know, harsh environments, radiation, humidity, hermeticity, all these things, thermal cycling. And that is traditionally, if you look into testing, that is what people refer to as testing, while characterization is more in the, let's say, fundamental device level. But yeah, sometimes people refer to that in the same way. And
at the end of the day, it's all about functionality. I love this slide. It really summarizes everything that we need to test in a chip. One thing that you said is that your customers come from different application fields, from automotive all the way to datacom. In automotive, we have in datacom we have the Telcordia standard, so it's quite very difficult, but at least it's standardized. In other application fields, there are no standards. How do you deal with that?
Well, on a case-by-case basis. And even in telecom, you don't think that everything would be standardized. So the Telcordia standards, actually, it's many years that they are not enforced anymore. People are drifting in very different ways. So you have things, for example, like the multi-source agreements for data center transceivers. Each of them has different standards, different requirements. It's not the same to test a component for, you know, like a long-haul telecom link where it needs to be an underseas for 10 years than a data center transceiver that is, you know, spendable after 2 years. So the requirements in terms of characterization and testing of each of these, let's say, application domains are very different. And to be honest, they are being built as we speak. And we have to sometimes discuss that with the customers themselves on asking them, what are your requirements? Because there are no standards at all.
We have a company in EPIC that they are masters in applying the standards to the testing and validation test processes. I'm going to go to Stuttgart together with my friend Iñigo. We're going to go together to Stuttgart to meet my other friend Andreas from RoodMicrotec. Andreas, how are you doing today? And most important, what did you think of the presentation from VLC? What kind of rooms for cooperation are there here?
Hello. Yes, there are many things said that are quite true. Maybe for the testing versus characterization. In my opinion, characterization is a thing that you test what the device really can do. So see the limits of the device. And testing is seeing if a device guarantees the limits you set. Normally the limits that the customer wants to see. And characterization is that testing that your device to get what your device really can do.
Andreas, what do you do? What RoodMicrotec does, and how we can find ways to cooperate between VLC, Rod, and ficonTEC?
Yeah, RoodMicrotec does indeed test wafers for a long time, and recently we have started testing at wafer level PICs, which do you see my slide now?
Mm-hmm.
Yeah, okay. We have started testing PICs at the wafer level, which is, of course, cost driven. The cost needs to be as low as possible. So we have a probe card that can connect electrical as well as optical I/Os at the same time. So a hybrid probe card that is manufactured from Jenoptik that Tobias mentioned. There is a fixed probe, no adjustment, and necessary, and it is implemented in a normal semiconductor wafer level testing workflow. So we are using an PXI system, as already discussed here, that is connected to a wafer prober, a standard wafer prober, and instead of a normal electrical probe card, we are using that hybrid probe card from Jenoptik. In the PXI system, there is electrical devices as needed, as well as different optical devices as laser sources, power meters, spectrometers, whatever, switches, and as well as external devices that can be connected. All of this is connected to the probe card, and we are testing electrical and optical signals and parts of a PIC at the same time at wafer level. So what we can do for you is that we are searching for new projects at optical testing, and what you can do for us is giving us ideas for no projects, new parts, new things you want to test, new ideas you have. That's what,
Andreas, bringing all the track record and knowledge on optoelectronic testing, entering the Interactive Photonics community, the way that you have done deserves an acknowledgement. VLC Photonics comes from the Interactive Photonics community, so there is obviously room for cooperation here. But I'm going to go now with all of you to Southampton, because my friend Milan Milosevic has something on his mind. Milan.
Hi, so I just had a question for VLC. I heard they are also doing like a whole bunch of wavelength ranges testing, so from near infrared to mid infrared. So I just wanted to ask, in terms of the mid infrared testing, what wavelengths are you targeting? because mid-infrared offers a variety of applications, for sensing and so on. So just interested, what wavelength range are you interested in, and are you doing this already? Is this process automated? And
so we are, to be honest, we have been mostly working on near infrared, so 1310 and 1550 nanometers, and visible wavelengths, mostly for biophotonic applications from 400 to 850 more or less. For mid-infrared, we have been exploring this with the local University of Valencia here, where they are working on silicon nitride for mid-infrared. And I believe that was mostly on the short mid-infrared, so in the order of 2.5, more up to, I think, 4 microns. So it's not something that our core expertise is there, and mostly because, to be honest, we didn't have too much traction from the market. So up to 2.5 micron, to be honest, is the only thing that we have been exploring up to now.
Iñigo, things are about to change there because the QCL price is gonna go down like crazy in the coming 2 years. So things are gonna explode. Actually, Anna is putting together the Mid-Infrared Alliance with all the companies on EPIC who have activity in the 3 to 12 micrometer wavelength, no, 2.5 to 12 micrometer wavelength range to be exact, to try to find a booming in this market that is gonna happen when the QCL price goes down, which is gonna happen next year. You will be aware of that. And with this, I'm gonna give back the floor to Milan. Let's go to Southampton. Let's go to Cornerstone. Tell us what's on your mind.
Let me share my screen.
You look fantastic with those AirPods. You are one of the stars in the wafer level testing at EPIC. It's great to have you here.
Thank you. Okay, can you see my screen?
Crystal clear.
Okay, so hello everyone. Thank you very much for the introduction. So my talk will be about germanium ion implantation into silicon for the wafer scale testing of photonic integrated circuits. So as we heard today, there is a whole lot going on wafer scale testing, and it's definitely a crucial component of any large scale manufacturing line, and it's critical for reducing the cost per chip and for maximizing production yield. So typical coupling techniques for wafer scale testing comprises using grating couplers that can be placed on a wafer on specific positions. However, this gives us a limited wafer scale testing capabilities because we can test the whole photonic integrated circuit. And as you can see in this image, if you want to test this component which is in the middle of the chip, that will not be possible. So we use germanium ion implantation to create a refractive index change in silicon. So as you can see here on the right, once germanium is implanted into silicon, it will cause the crystalline lattice damage and increase the refractive index of the implanted material. Then we can use annealing. So this can be, for example, RTA annealing, electrical annealing, or laser annealing to decrease and trim this refractive index, and this actually represents the core of our technology. So if we want to, for example, test this component in the middle here, we need to use germanium ion implantation to create temporary test points. So these test points are introduced, for example, in the form of grating couplers. Once we introduce grating couplers, we can couple light in and out of the circuit. We can do our wafer scale testing, and then we can use annealing to erase these temporary test points without affecting the optical performance of the overall circuit. Currently, since we are implanting silicon, there are some residual loss after annealing, about 0.1 dBs. And because of that, we developed another technology which gives us the opportunity to implant, for example, the slab, the silicon slab layer, and create directional couplers. So if you see here on the bottom, in the bottom slide of this image, you can see that we can actually taper. We can tape the optical signal using this directional coupler to a waveguide, and then we need to find some dead space on the chip. We can place our standard grating couplers and do the wafer scale testing. After we finish with the testing, we can simply erase this directional coupler coupler, and there is no residual loss after annealing. So we have patented this technology, and we also published a lot of papers on this. So if you're interested, please have a look or just send me an email. We have also used the same technology to perform automated circuit repair to trim, for example, ring resonators and Mach-Zehnder interferometers, or for example, to do electrical annealing and create some one-time programmable photonic circuits. So I'm not going to go into the details about this, but here are some papers where you can find more about this. In terms of automation, we have been working for a few years with ficonTEC to bring this technology from lab to practice, and we have developed a vapor prober, which can be used for mixed signal electro-optical testing, for chip and wafer scale testing, for automated optical inspection of the wafer, data analysis, and so on. And we managed to test a lot of devices on the 8-inch wafer. And here in this image, you can see both optical and electrical probes positioned on top of our 8-inch wafer. What we can offer is through the Cornerstone Foundry, we offer deep UV lithography service for 3 SOI platforms, so 220, 340, and 500 nanometers SOI. We have a really experienced and large team, so we provide design consultancy and bespoke training in partnership with Lucida Photonics, wafer scale testing, and also bonding. If you want to know more about MPW schedule and cost, please visit the Cornerstone website. Our technology was recently featured by the Optical Society of America, and we are very keen to continue working in this area. We are looking for collaborations with the industry and with academia. So we invite you to use our technology and to tell us more about your technological challenges so that we can actually work together and to create a roadmap on wafer scale testing for photonics in general and silicon photonics as a whole. In terms of challenges, there are a lot of challenges on various levels. So as I said, there are a lot of applications for photonics now. They're expanding beyond datacom and telecom. So definitely we need to find a way how to reduce time to market and costs. And definitely we'll need some built-in self-test, generic test protocols, inline testing and control, and photonic chip programmability. So if you want to find out more about what we are doing on wafer scale testing and also about other projects, please register for our virtual showcase event, which is scheduled for 14th of December. And also I would like to thank you all for your attention, and to my colleagues and for their help and support, and also to the EPSRC and the Royal Society for funding. So I hope I'm within 6 minutes, and if you have any questions, please feel free to ask. There are a lot of things to do, I think, in general.
Thank you very much, Milan. Super interesting presentation. Maybe you can elaborate a little bit more about the possibility to repair failed chips.
Oh, yes. So, I mean, I don't want to, maybe I could actually share my screen again, because
yes,
I have one interesting slide on that. Let me see. Oops, where is that? Okay, can you see now?
Yes.
So as you know, I mean, silicon photonics devices are very sensitive to, some of them are very sensitive to wafer thickness variations, and also, to fabrication process. So one particular device can be ring resonator. And ring resonator is very sensitive to fabrication process, wafer thickness variations, and it's very difficult to position accurately the operating wavelength, the resonant wavelength peak position. So what we are doing, we can, for example, implant this spacing between the waveguide and the ring resonator. And then by annealing this via laser or electrically, we can trim the coupling efficiency and insertion loss of the ring resonator. And if we implant this in this green area, you can see this area of the ring resonator, very tiny, 6 microns long area, we can accurately position this resonant wavelength peak to a target wavelength. So for example, in this case, you can see target wavelength was 1550 nanometers, and we managed to position this. This was done by the way, manually. We managed to position it to 1549.93. We have done a lot of testing of ring resonators, and we always managed to position ourselves within 3% of the targeted wavelength peak position. Similar things we did with Mach-Zehnder interferometers. So we managed to achieve a phase trimming with accuracy of 0.01 radian. But this work was done back in 2018, and it was done manually. So now, since we had an excellent collaboration with ficonTEC, we managed to make this wafer prober running. So I think if we do the same with the wafer prober, we can achieve much better accuracy.
Milan, we've been talking about this already for quite some time. The erasable gratings is now a mature process with automation already. Will CMOS foundries implement it, and what do you need to get there?
Well, when we talk with the industry, when we talk with industrial colleagues, they were relatively worried about erasable gratings, although I know that you are a big fan, and I also like erasable grating couplers. So one worry was that once we erase them, we end up with a residual loss of 0.1 dBs. So for certain applications, this may create a problem, especially if you want to test a lot of components on the chip. And secondly, as you could see from my slide, in order to couple light into the grating, you need to taper it. So this taper may add a little bit to the overall complexity of the photonic circuit. So the industry, actually particular, not all of them, but some of them were a little bit reluctant to implement this for their testing scenario. So recently we have patented the same technology, but with erasable directional coupler. So now we don't have any residual loss after test. And I hope, I really invite everyone to use it. And
we have Globalfoundries later in the program, so we're going to push them like crazy.
So
we're going to push them like crazy.
We can do the test.
We have a person from the Space Photonics with something on his mind. Ahmed from Leo Space Photonics. What's on your mind?
Hello, everyone. Can you hear me?
Yes, loud and clear.
Okay, so first of all, I just wanted to ask, Milan, how repeatable is this process? I mean, can someone just do the amorphization and then delete everything? I mean, annealing. Can you do this cycle? How many times? Is it repeatable? Do you get to destroy the wafer after a certain point?
Okay. So hello, Ahmed. I'm very happy to see you again, because Ahmed was a member of our group, until recently. So yes, we can do it very, very precisely. So either with with a laser or electrically. So we managed to use the laser to do this wafer scale testing, and with the laser we actually got a little bit of issues with a certain power of the laser. So we tested devices with the laser power from 60 to 95 milliwatts. So if we were in between of that range, it was a little bit difficult to accurately control the level of annealing. With electrical annealing, which we are developing now, we are hoping to get better results. So far, everything works fine. So for example, for electrical annealing, if we anneal it with the voltage of 7-8 volts, then we can definitely destroy our devices. But if you apply voltages which are less than that, for example, 4 volts, 3.5 volts, everything works fine. And since we have this wafer scale tester, now we can do both electrical and optical testing at the same time. So we can, for example, vary voltage with a step of 50 millivolts, and then we can achieve really gradual change in optical performance of silicon photonic devices. So I think in terms of reliability, it's fine.
Milan, question
We're
from the
certainly right.
YouTube universe. We have Gregory Finn
Yes.
from ficonTEC. Where does Cornerstone 2 take up from the previous Cornerstone?
Okay, so for Cornerstone 1, you can find a lot of details online, and we offer this definitely passive device fabrication and some active heaters and modulators on 3 different platforms. But of course, Cornerstone 2, which is now running, is trying to address some new challenges in silicon photonics, because the global market of silicon photonics expanded. I mean, we are now talking about different applications. I mean, sensing and LiDAR and so on. So now we are working on different material platforms. So previously we had only SOI, 3 different thicknesses. Now we're also working on silicon nitride. We are working, of course, on mid-infrared applications for wavelengths between 4 and 12 microns. And we are trying to come up with a really nice scenario where we can actually produce devices that can be used for both near and mid-infrared ranges.
I am very excited about the mid-infrared.
Cornerstone 2 is also dealing with bonding, so laser to chip bonding as well. And the whole team, I think, expanded a lot.
So the Cornerstone 2 is really growing into the shoulders of the champions, offering heterogeneous wafer level manufacturing and packaging. And with the team that you have together, Graham, you are watching, Graham Reed, it's great to see you. You have gold in your eyes. Continue in that particular path. I would like to ask you one more question from the YouTube universe as well. You have been for 3 years automating the process, working with ficonTEC. Is there any lessons learned that you could share with the community, because we all want this to happen more often?
Well, definitely. I think first of all, thank you, Jose, for introducing us to ficonTEC. I think it's
that's all I wanted you to say.
example of EPIC bringing together its members. So we had a really wonderful journey with ficonTEC, and I think because it was, I think, our first project, and also ficonTEC's, because ficonTEC was mainly working on assembly and packaging. We could certain things we could speed up, but I think in the future this can be really overcome. So we managed to proceed with electrical and optical testing, but I think the next stage we need to go to proceed with the high-speed testing and testing, modulators and more complicated devices. Of course, what we did is what we could do, because of course we had a limited budget. So I believe that ficonTEC or any other company who would like to invest more could make a much better deal of this wafer scale testing. I mean, they can possibly add several electrical probes, a lot of optical probes, fiber arrays, and do like a huge general testing, of the whole wafers, and of course many devices in one go, I think.
Okay, thank you very much, Milan. Super interesting presentation and discussion. And now let's move to the next speaker. And yes, thank you. Let's move to the next speaker. So the next speaker is Ken Giewont from Globalfoundries. Thank you very much, Ken, for agreeing being here. I mean, we know it's very early for you. So yes, if you can share your screen, the floor is yours.
Okay, is that coming through? Go full screen.
Yes, if you can go, yes.
How's that look? Okay.
Now, thank you.
Okay, yeah, thank you for the invite to talk at this meeting. My name is Ken Giewont. I work in Fishkill, New York at Globalfoundries in technology solutions. Been focusing on the silicon photonics platform development here now for several years. I also want to thank Barry Blakely. He's the manager of our silicon photonics test department. I think he's also on the phone. He helped put some of this material together. So I have 3 slides I'm going to share. I want to give a brief overview of the technology that we offer. And this is important because in addition to developing the process technology that went with our platform, we also had to put a significant amount of effort into developing test platforms. And so we have 2 technologies. One 9WG that is qualified for production today. We are in the process of developing a few more features this year into early next year. It's a monolithic CMOS technology that includes, it's focused on O-band, but we also do offer a C-band library, passive V-groove fiber attach, and a full cadence PDK library. The second technology that's currently still in development, it's called 45CLO. This leverages much of what we've learned on 9WG. It leverages a lot of the same T-silicon, leverages a lot of the same PDK device elements, but it does add higher performance monolithic CMOS. It's a 45 nanometer based RF CMOS. Then we also added silicon nitride, copper pillar receive pads. And then we're going to be continuing to develop further features this year into late next year, including micro ring modulators, UWDM, sealed undercut heaters. So again, I want to emphasize, besides this, all the investment we made in the process technology, in the base device development, we also had to develop quite an extensive silicon photonics test capability. So just a snapshot of our device library. This is an example of 45CLO, but 9WG would look very similar. We do all of our testing through the top gratings. We do a lot of focus on wafer level testing, high automation. We do have to test not only the photonics, but also because we have integrated CMOS devices, both reference designs, full back-end passives, front-end passives. So we have to do plan testing for CMOS, high-speed modulators, ring modulators, detectors, and then a full suite of passives. And we also have polarization control on the PIC. Our primary fiber attach method is using V-groove fiber attach. It's a passive alignment. We do have the ability to put gratings in these regions of the V-grooves that are sacrificial. We heard about erasable gratings. We have the ability to put the top gratings in these areas where the V-groove is eventually placed. So we can do some level of PIC testing prior to the V-groove on a sacrificial grating. And then we've also, still in development, we are doing direct laser attach to place directly on the PIC. So again, a really broad suite of devices in our PDK library. It does offer quite a challenge for testing because we do have to test all of these devices. We have to develop PDK compact models and then develop a wafer acceptance test for manufacturing. And so it does present several challenges in PIC testing. I want to spend most of the time on this slide. So Globalfoundries, in addition to developing the process technology, like I said, we've also invested heavily in silicon photonics test capability. On the left side here, we focus a lot on wafer level testing. For technology verification, building our compact models, it's not a fully automated, I call it a semi-automated system. Primarily two fiber tests. There are some fiber bundle capability, but the capability here really is focused on full O band and C band characterization through temperature, and also adding the analog bandwidth capabilities to build our compact models. The workhorse of our testing is what we call our ILOTS tester, inline optical test. Again, it's focused for volume testing, wafer level, full automation. It is used primarily for early process development. The fact that we can gather a lot of statistical data very quickly, very helpful for analyzing process development, wafer level splits, but it's also then leveraged to monitor the process. So for wafer acceptance criteria, process monitoring, and then we do also use some of this data to feed back to our PDK compact model development. We've expanded some of these test systems to also include special AC testing for S parameter, EO, and OE controls, and we recently expanded this to collect NRZ and PAM4I diagrams, and expanded some of this for fiber array block testing. Both these systems are primarily used for our PDK P-cell development, but more recently we do support custom designs, so customers who want to come in and use our foundry and they want to do their own custom device design. We do offer the capability to have them place their custom devices into our standard, what we call an ILOTS pad cage, which includes both electrical and optical probes. And then, so not only can we monitor our P-cell PDK devices, we could also offer the service to monitor a customer's custom devices. So that's an area that has grown over time. But this test system, these test systems here are the workhorse of the test development team. And then for testing PICs and more functional wafer level functional test, we also offer as a service to test PIC products. We have a low speed system which tests both electrical and optical testing, separate probes, one for the electrical, and we have probes for the optical. And this also uses a sacrificial grading option that I mentioned, where the grading is placed where the V groove will be placed in the future. And then that after we do go back to do the V groove processing, the sacrificial grading is then removed. So this could offer a volume level, wafer level sorting for customers' products. And then there's a fourth system that's optimized more for higher speed testing. So high frequency up to 67 gigahertz. It could also be used to characterize TRA or drivers that are on the chip. And then it has a full suite of single-ended or differential S parameter characterization. And this could also be expanded for fiber array block characterization. And so this is also offered as a test service to customers. And then finally, on the far right, full characterization at package level. So MCMs at speed performance for early customer bring up, EOH bring up. This is both for O band and C band coherent applications. And so again, the emphasis on really leveraging the wafer level testing for both technology development, PDK modeling, but then using the same systems for automation and process manufacturing controls. So with that, I'm gonna end my talk.
Thank you very much, Ken. Super interesting presentation to see all the processes that you are able to do in Globalfoundries. We have a few questions in the chat, but first of all, I would like to ask you, is there any kind of collaboration that you could be looking for in order to overcome any challenge in your testing processes?
Well, I would say, Barry and McCormick's test team, they do a lot of in-house development of both the probe cards and the software and the test equipment. I don't know, Barry, are you on the phone?
Yeah, yes, I am, Ken.
Do you want to comment on what you think? There's any opportunities for collaboration with this audience?
Yeah, there may be. We're a pretty good position right now on our automated test systems. So, we're not looking for outside help, but there are challenges that some of the prior speakers have mentioned, particularly like testing in parallel. That is very challenging aspect. We're not doing that today. We're testing one die at a time. And then, just overall speed and efficiency in the test process is areas that we're focusing on.
Yeah, and if I could add, I mean, one area, I know, like I said, I think most people do most of the wafer level testing through gratings. And of course, once you get to the product level, you're either coming in, through either V-grooves or maybe die edge butt coupling techniques. And so that's a really, challenging divide, so if there were wafer level test techniques or probes, optical probes especially, that could, laterally go into, like, I don't know if you're familiar with the V-groove. I had a small picture on it on my second page, but lateral probes that could test a V-groove mode size converter at wafer level, that would be very valuable to us and to customers, because currently right now we can only fully characterize that fiber interface after dicing and after a fiber attach process. So that's one area that I know I've seen some papers on, vertical probes with a bend, but that's one area that I could think of.
Okay, very good. So you are looking for faster, and cheaper testing, So, well, let's see what we can do here at the PIC for you. So maybe I can give the word to Tobias from Ignazio.
Thanks, Anna. Yeah.
On that.
If we go to Tobias and then we go to you, Ignazio. Thank you.
Or Ignazio, please. You are the senior. go first.
Go ahead. You are the young one. You first. I'll follow.
Okay. Thank you. Yeah, very nice. I imagine Ignazio and me, we might have the same question. So you have shown quite some impressive integrated or embedded systems for testing, and also working on the on the packaging automation. My question is, what is preventing you from kind of scaling it up yourself? Is it the automation effort behind it? And well, if there was, let's say, an open access development framework very intuitive to use, could you imagine using it for integrating your embedded systems, well, as tools to scale up more?
Well, when you say scale up, I mean, we do offer full characterization of our PDK devices and our PICs, but as a service to a customer, scaling up, there's always there's a pretty big demand now for not only characterizing our devices, but now more and more customers are doing custom designs in our platform, and we do offer it as a test service. And so that is one area where it has putting a lot of strain on our internal resources to then start to take on more and more testing of the customers, because they're going to bring in their own set of devices they want to characterize. So that is one area that we try to manage it by forcing the customer into a standard pad cage so that we can use our standard probe cards, our standard test algorithms, but there is still that extra resources needed to debug each customer's set of devices, either discrete devices or blocks of PIC functionality. And so that divide between them taking their device level characterization into a PIC and scaling that up into a product characterization, that is one area that we can only do so much with the equipment and the people we have.
Mm-hmm.
As they scale up into production, that is a challenge, and that so then that becomes whether we have to invest in more capacity for that customer or we start to look to go outside to an OSAT.
Okay, so it's the high mix of your customers that's giving you some challenges and the limited resources internally that you have.
Yeah, and we definitely want to offer the test services. That is one area that we are interested in doing. So not only just selling wafers, we also want to sell the test service.
Mm-hmm.
So and that's a balance between when to turn that corner and offer more of those services.
Okay, yeah, I'll drop you an email. Maybe I got something to show you.
Yeah. Okay.
Perfect.
Yeah. Very good.
Thanks.
Your name was
Tobias.
Tobias Mueller. Okay.
Yeah, Tobias Mueller.
Don't worry, we will make sure we will make sure that you connect after the meeting.
Thank you,
Ignazio.
Okay. Yeah. Good question. Thank you.
Ignazio, would you like to add something?
Yes, Ken, thank you for your presentation. And without getting into NDA issues, one of your customers and collaborator, Ranovos, is also working with us on some R&D projects in Germany. And one of the issues was correctly sort of addressing the need to test optically electrical chips. And you have your beautiful technology for V-groove fiber arrays. So I don't really have a question, but listening to your speech, we are working on this, and I will simply get back to you after this epic event with some more specific questions. But we are addressing within our R&D programs both the needs of simultaneous chip testing, so more one chip at a time, as well as dedicated probe beds that can address both electrical and optical. One question I have, however, is that what I've learned in recent times is that RF is more challenging than coupling optical signals. Optical signals can travel in and out automated equipment quite easily, while RF in the few gigahertz, in the tens of gigahertz range, is quite difficult in terms of connectivity to automate on large scale. So could you comment maybe on this? Do you see a near future where we will use optical signals to bypass the difficulties of de-embedding RF probes, for instance, or having to deal with the complex and expensive RF probing?
Yeah, that's a good question. I'm gonna pass that question off to Barry Blakely. I know he also manages the RF test team, and I personally have not. We have not been discussing, or at least I have not been in discussions with leveraging optical signals to solve some of the RF testing problems. But perhaps Barry has some comments here.
Yeah, thank you for the question, Ignazio. It's a good one. So luckily, we have been playing in the RF space for over 20 years. And we have been doing production level testing of RF components for that long, and have perfected a number of systems. Again, we design and develop our own testers. We also, have our own in-house calibration methods where we can calibrate right down to the probe tips. And today we have just about 20 RF testers running on our production floor 24/7. And so when we started working with some of the silicon photonic components that required some RF testing, like evaluating TIAs and drivers, that was pretty standard stuff for us. And so we've successfully been testing number of TIAs and drivers for the past few years, and have managed to integrate in some of our optical testing within that same system. And there could be in the future, I tend to focus more on developing the test solution, so I'm not always up with the latest on replacing some of the RF type circuitry with optical, but we are expanding our optical test capabilities every day, and would certainly welcome the challenge of providing more optical type test. So I'm not sure if I answered your question, but if you've got another specific point you're interested in, please shoot.
No, I think I will. We're getting to very sort of specialized details here, and I don't want to hog the time of the event. But thank you for your answer. I'll certainly be in touch. Thanks again.
You're welcome.
Okay, so thank you very much for this discussion. We have another question in the chat. So Francois from iPhonics, would you like to make the question by yourself?
Sure. All right. So I see that sacrificial V-grooves, surface gratings over V-grooves are being popularized, and I also see that there is a common need amongst several people to test at wafer scale using production coupling, which is likely not to be surface gratings. So would it be advisable to start working together on some form of a standard way of testing at wafer scale from the top using probes that can descend into V-grooves or U-grooves?
Yeah, that's exactly on actually at the first question. That is one area that if that could be developed, I know that would be very valuable to us. I know one challenge is also testing in air, because our V-groove with our mode converter is designed to be index matched. You could put IPA in the V-groove for a bench test, or at die level you put index matching epoxy into the fiber. So that also is another challenge when you're testing in air at wafer level and in volume. I'm sure you can't do any kind of index match, so you'd have to compensate for the added loss. But even if you could compensate, that would still be very valuable. Being able to test through a butt couple, even if it's not a V-groove, a lot of customers would use deep rye at the edge of the die with alternate, maybe inverse taper coupling at the edge. Any way to test through edge butt coupling would be very valuable at wafer scale for sure.
Okay, thank you for this discussion. We have another question in the chat. So Milan from Cornerstone, do you want to ask by yourself?
Yes, thank you. Thank you, Ken, for a very nice presentation. So my question is maybe a little bit off topic because this meeting is on wafer scale testing. But I thought to ask you about your thoughts on 1310 versus 1550 nanometer integrated photonics. Mm-hmm. So can you comment on costs, laser stability, performance, and so on? Because here I can see we are working a lot with the industry, and most of the industrial partners are working on 1310 nanometers, but academia is still focused, in my opinion, on 1550 nanometers. So do you have any thoughts on?
Yeah, I could comment. It's a good question too, because we struggle with it quite a bit. You know, clearly the bulk of the customers are still in 1310 O band, but there is I'd say a consistent smaller percentage that still require C-band. You know, the data center to data center, of course, any coherent applications, and there's even, you see C-band applications now moving inside the data center. And so all of our PDK development, most of our PDK development is still O-band, but we do offer a C-band library. It's not fully qualified. We have a prototype library that we're going to continue to develop, eventually develop and qualify in 45 CLO, because C-band's not going to go away. It's clear. And so it just hasn't been our workhorse. So we've been emphasizing an O-band, but we still see the C-band demand is there. Again, the volume is not as big, but you know, but the ASPs are typically higher. So, you know, that's something that we don't want to ignore.
When I see this, I am amazed. I am amazed of all the different things. This is like my dream list, and you have achieved everything. Of course, we could talk about this slide for years, but let's just do it for a couple of more minutes. When you do the high frequency testing, you go up to 67 gigahertz. So EPIC is working very, very hard on the beyond 400G. And in the beyond 400G, we are going to integrate 70 gigahertz modulators for multiplexing 100 gigabaud channels. That's in the roadmap. Why did you stop at 67 gigahertz?
Unless you want to fund the next, well, I think it's just really the capability of the test equipment that we have today. Clearly our roadmap to go beyond that is there, right? It's just, you know, Barry can comment, but it's really where the capability with the equipment we have today puts us. But clearly we understand there's need and roadmap to go further. Yeah, and Barry, go ahead and comment.
Yeah, no, that's true. I mean, right now that 67 gigahertz is equipment limitations, and but it's fine for some of the work that we've been looking at, some of our modulators and you know, photodiodes. We've been characterizing them, you know, up to 50 gigahertz, and so it's enough bandwidth to do the work, the development work that we're trying to do. But I agree. In the future, it's going to go up.
And the future is the day after tomorrow. So the future, we already have challenges. I invite you to join our upcoming meetings on Beyond 400G, because the future is very, very, very close, very nearby. Thank you so much, Globalfoundries, for this. Keep coming. I'm going to go now to the next speaker. I'm going to go to the beautiful city of Ghent, one of the most beautiful cities in Europe, but one of the most innovative places for silicon photonics in the world. Wim Bogaerts, who we know each other for a long, long time. Wim, thank you very much for being with us this beautiful afternoon. It is 4:37 in the Netherlands and Belgium. The floor and the attention of everyone goes to you. I have you muted. Let me unmute you. Yes.
Okay, I'm unmuted. Thank you. I won't share my screen, so if you want to see what I'm presenting, you will have to put my webcam full screen, because I'm basically just sitting in front of my presentation. So, and I'll move myself a bit out of the way to talk. So what I'm going to talk about here is not as much the technology we have for testing, but the needs that we can see in the future. Because what we're working on now is, let's call it the next generation of photonic integrated circuits, programmable photonic integrated circuits. Just a few words of background. Who are we? Well, I'm part of a group, a research group in Ghent University and IMEC, the Microtechnology Center in Belgium. We've been working in silicon photonics now for like more than 20 years. And mostly on, well, originally mostly on communication applications, but nowadays we're working on sensing applications, biomedical, etc. Maybe an interesting thing to know is that already 10 years ago, we were one of the first groups in the world to start automating testing. So we installed a fully custom built wafer scale tester in our clean room in 2011. It took a couple of years to actually build it, but we were operational in 2011. But what I see now in this meeting is that testing capabilities have increased dramatically, and that's needed. Because what we're looking at in photonic circuits, and I think that has fallen or have been mentioned already quite a bit, is that it's no longer just about the photons. Photonic circuits nowadays can have tens of optical IOs, which you can address with the fiber arrays. But we also already see that we have RF signals in transceivers, but also in microwave processing. And then circuits become ever more controllable. So you have lots of tuning elements on that circuits, and we're looking at thousands or maybe hundreds or thousands of electrical tuning elements on the chip. Now, a programmable circuit is a very special kind of photonic integrated circuits. It's actually, the idea is that you make a photonic integrated circuit that is generic. Compare it to a field programmable gate array in electronics. It has not been designed for any specific function. It basically consists of a set of input and output ports, which are connected with waveguide meshes that can all be individually tuned. So all the couplings between the waveguides can be tuned to route the light wherever you want, from any input to any output. Now, such a circuit can only work if it's fully controlled. So there's no point in incrementally probing every individual building block, because you can only test that circuit if every element is connected. So that's quite a challenge to test these circuits. Just some example, this is a circuit that was done by MIT and Elenion a couple of years ago. And you see it has already like a ton of wire bonds on both sides to control every tuner. And the circuits that we're looking at in the future are an order of magnitude more complex. So this is an example of a large scale PIC that we've been building in the framework of the Morphic project. And it has 3,300 DC connections that need all to be individually connected. So that's kind of a challenge. Also, it has 72 fiber inputs. It has 12 RF inputs and 12 RF outputs, and all of these have to be contacted. So why would you make such a circuit? Well, the whole idea about these programmable circuits is that you dramatically speed up developments of PIC products. For instance, instead of having to go through the 5 months to a year development of a new photonic integrated circuit, you essentially cut your supply chain in half, and now you can get off-the-shelf circuits to implement whatever you want to prototype. Now that's a good idea, but for that, these programmable PICs need to work, and they're quite complex. So you need good test and characterization equipment somewhere in that flow, in the early part of the flow. So that means that you need to be able to probe your programmable PICs, like not just tens, but like hundreds or thousands of DC connections. You need to bring in your RF probes, and you need to bring in your fiber arrays all at the same time. Now, these are all problems that have already been mentioned several times by quite a lot of people here in the meeting. So it's maybe not new, but the scale on which this is needed in the future, if you want to enable this kind of general purpose, massively tunable programmable PICs, then you need to bring everything together in a very elegant form factor. So that's basically my story. So I didn't come here pitching solutions. I've come here to pitch my needs. If we want to pull this off in the future, if we want to build something like real photonic FPGAs, we need that testing capability. Thank you.
Thank you very much, Wim. So, well, great presentation, a great challenge. So we have a few questions here in the chat. So Ignacio, I think you have a comment.
Thank you, Wim. Well, really fascinating stuff you're doing at IMEC, but I knew this already, and somehow this connects with my early days when FPGAs were the novelty. First a comment, and is simply that you just gave a testimony on what I call the convergence between semicon and photonics, where the two worlds will merge, and that is really the future. The other comment is that, again, I mean, you have one of the most challenging challenging needs, which is exactly what I was trying to target in my early speech, where you combine high count pins, high pin counts for the electrical. You have RF input output, and you have arrays. So that is what will require a lot of development, and I believe is not yet on the market. One of the reasons is that photonics has been a small fish for the big giants of semicon. So nobody will really invest a lot of money to test a few wafers, a few wafers of photonic stuff. But I see the solution will be coming. Maybe I'll be long retired when you get them, but but definitely the volumes are growing, and I believe that what really will make the volume coming is this convergence I was mentioning, like chiplets, photonic chiplets being embedded into conventional semicon, up to the point where the two worlds will merge completely. So this was more of a comment. I'm not offering a solution yet. I certainly would like to hear more. So we need to talk. Thanks a lot.
All right.
Okay, thank you very much for your comment, Ignacio. Also, we have a comment from Tobias from Jenoptik. Tobias, do you want to make a comment by yourself?
Yeah, as I mentioned earlier, we have the possibility to arrange a 2D layout of several optical in and outputs, and currently the standard is 16 optical in and outputs on an array, but in principle we can do it, as I said, on a 150 millimeter diameter. So we haven't done it yet, but I would love to test it on maybe such a solution, or even go for optical switch testing. So that would be kind of sweet spot for our solution.
All right. Yeah, we should discuss further.
Oh, sure. I mean, so I see room for collaboration here, so we will make sure that you get an introduction after the meeting. Now I would like, well, let's explore other options. So I think we have here Adrien from Teem Photonics.
Hello, yep.
Hello. So maybe I think you can now talk about what are the approach that your company is developing, and maybe do you have a slide to show us?
Sure, let me just share it and go full screen. So you should be seeing it now.
Yes, very good.
Okay, great. So thanks for giving me a minute to present actually some technological results we've got on the MASTART consortium. So a few words of context. MASTART is a European funded project that aims at manufacturing, like mass manufacturing transceivers in Europe actually. And so Teem Photonics is part of it, as well as Leti, ficonTEC, and a few others, in fact. At Teem Photonics, we manufacture photonic integrated circuits on glass, and our products, they include interposers for fiber to PIC coupling, so several solutions for several type of coupling. We call them WAFT, and we've had the idea to adapt some of them to edge, like wafer level testing for edge coupled PICs. So basically, we have a range of WAFT that are usually made to deflect light into grating couplers, but we said, okay, if we just butt couple these devices to edge couplers, that might work as well. So we've performed some tests together with Leti. And so they have this specific process that was mentioned earlier by Globalfoundries, where they deep etch a trench at the edge of their chips before dicing. So if you want to access these edge couplers, you need to dice the chips. And so far, they had no other solution to test advanced building blocks like broadband AWGs, or you can even think of micro resonators for frequency comb generation and whatever. So we've provided them with these WAFT, and they've set it up on their PI wafer prober. Turned out it worked well, at least with one channel. First light was easy to find. They could measure an optical spectrum like in the O band, covering the full O band. Actually, everything that the grating coupler on the other side could transmit. And it really pushed us to move forward now with multi-channel testing. So we're going to provide them soon another WAFT with up to 8 channels. We could go like to much higher channel count if needed. So yeah, that's pretty much the technical results so far. So I'm interested to get the feedback from foundries and design houses to see if there is an interest to. But I've got part of the answer from the previous talks. And on our side, we can, well, the advantage of our glass platform is that we can mimic more or less the silicon photonics IOs, so adapt the pitch and so on. We could even provide components for visible range testing of nitride, for instance. And since we are component makers, we need some help to get that on a probe, obviously. So yeah, that's pretty much it. Thanks.
Okay, thank you very much, Adrien. So yes, well, any company that want to contact Teem Photonics for the challenges that they just presented, please contact me and I will make sure you contact them. Thank you, Adrien. And also, well, we didn't talk, we talked a lot about wafer level testing, but we didn't talk about burn-in testing equipment. And for this, we have here Dylan from Yellow. Hello, Dylan.
Hi, Anna. How are you doing? How's things?
Maybe it's a good moment for you to introduce the capabilities of Yellow for burn-in testing.
Yeah, for sure. I mean, for those of you who don't know who we are, Yellow are essentially, yes, as Anna said, we manufacture laser diode, burn-in, life tests, LIV equipment, characterization as well, laser diode characterization equipment. Essentially it's for, we do it in large volume. We do it for any type of laser, any type of package. So we do it COC level, VCSEL, we do bare die package level. And I think, you know, at the moment we're doing it at that level now, but there's been a lot of talk today, obviously, about wafer level, and that's something we're looking towards for the future, because there's been a lot of talk today about wafer level testing, but wafer level burn-in is a different sort of challenge, and there's a lot of probing and sort of thermal challenges that come with that. So that's kind of where we're looking at for the future. But yeah, in a nutshell, that's basically what we're doing.
Thank you very much, Dylan. So, well, anyone that wants to contact Dylan to know more about the burn-in testing, please send me an email and I will make sure that you make the introduction. Okay, and now let's move to the last talk of today. So it's my pleasure to introduce you Nazanin, Business Developer Manager at Smart Photonics, to talk about what is required in indium phosphide chip testing. So Nazanin, hello.
Hi, Anna. Thank you for the introduction. Let me share my screen here with you. Can you see my screen here?
Yes, very good.
Full page?
Yes, yes.
Okay, perfect. So maybe it's best if I start with a little introduction on Smart Photonics. I'll keep it very brief, as I'd like to get into the topic of testing. So at Smart Photonics, we are a foundry. We are a pure play foundry, and we manufacture photonic chips. And these chips we manufactured on indium phosphide-based substrates. As a company, we've got more than 40 years of technology heritage. We come from Philips and Technology, University of Eindhoven. So we've got the two main pillars being the research and the manufacturing covered. And for those of you who've heard, recently we've got a 35 million euro investment. Now, we obviously like indium phosphide, but we get even more excited when we see different reports acknowledging that it's one of the advanced platforms for using or manufacturing PICs for the different reasons, being high performing, lower cost and size, and lower power consuming chips. Now, obviously, PICs come in different flavors, and they are used for different markets, be it datacom, telecom, for sensing, for medical and biomed, for LiDAR, with the development of autonomous driving. But regardless, you know, you've got the different platforms that you can make use of. At Smart, we offer the MPW, which is just a lower threshold access for introducing new technology for smaller companies, or the full-on wafer dedicated chips, or dedicated wafers. Now, obviously, depending on the requirements, either full wafer testing or on-wafer testing or die-level testing would be required. One important topic that I'd really like to address is just the cost. A huge portion of the cost, when you break down the cost of the PICs, is packaging, testing, and assembly. Now, if we could allocate a whole bunch of that testing at a wafer level, that would, and have it standardized, obviously that would help the customers on the cost that they're bearing on the testing side. And aside from that, I think something that was mentioned earlier was, should we be doing testing on all the dies at a wafer level, or should it be just sample testing? And to me, my personal opinion is that it depends. If you talk to a company like Facebook, they seem like they have a lot of problems with their dies. Now, maybe their yields are low. And if the yields are low, and if the cost of packaging and assembly is high, to me, it makes no sense not to be doing every single die testing at a wafer level. But the flip side is that if relatively you've got fairly high yield on the wafer, and depending on what you're making, packaging and assembly costs are lower, then maybe you can do a test. You can do a subset of your wafers, of your dies on a wafer, and test those. But that's definitely something to consider. And I think the standardized packaging, if it could be offered, that would definitely help customers in the long way. Now, at SMART, we ease our testing part because we do essentially all electrical level testing on our wafer. Maybe I'll just play the video here. So it's fairly rapid, but obviously it'll require standardized pads on individual dies so that this can be done. Now, not only do our customers require to have electrical testing done, sometimes they would even ask us to put active layers, even if they don't necessarily need it for their systems. So for example, they can have sacrificial light sources so that this is just for testing purposes, right? And if, again, that level of testing can be done on wafer level, in the long run, it would help bringing down the cost. Now here on this slide, it's a very busy slide with a lot of pictures that I've got here. On the very left, I've got schematic pictures of the chips, and then I've got a real picture and some of the testing that's done. Now, when we talk about PIC testing, what are we actually testing? There's two things or two ways that we could be testing a device. We could be testing on a parametric level. So we could be checking for the basic functionality. And that would be very helpful if you're looking at this bottom image. If you've got here, you've got 3 centimeters of waveguide, and we've got a pretty nice laser. But obviously, one thing that's nice to measure is what's the insertion loss. Now, here in this image, you can see, well, it's not that high because otherwise you couldn't get peaks that's this sharp. But the fact is, you're wanting to know what the losses are between the actives and passives, how much reflection there is between the interfaces of the actives and passives. And again, in this case, it's not much, but those are definitely things that needs to be measured. This is an example of parametric testing. There are other tests that could be derived from some of these optical parameters. So it could be passband, it could be finesse, it could be FSR, it could be peak positioning, on-off ratio. And again, on my slide, you see a number of different tests. So for instance, you could see the power density as a function of wavelength here. Or the second testing that can be done is the functional testing. So a good example would be the eye diagram that you see on the top right. And in this example, you're looking at a 100 gigabits per second transmitter. And here, because we're looking at a continuous sweep, tunable laser, obviously one thing that would be ideal is to make sure that there's very little power change, right? So these are some of the examples of the testings that would be nice for our customers to do. Maybe worth mentioning in the second one, just here you're looking at a long range tunability with fairly high SMSR, right? So any one of these parameters that would help the customer identify if it's a good die at the end of the day would be very helpful for them. Lastly, I'd like to stress that testing is really essential because sure, we start with the design with the PDKs to come up with a design for the foundry for manufacturing, and then we pass it on to testing. But everything has got a feedback loop. So from testing, we can have a feedback loop towards the design to optimize our PDKs. We can have, again, feedback loop to the manufacturing to identify what are the tolerances, what's the window for the customer, right? For the key parameters they're looking at, right? Those tolerance windows can be larger, can be smaller, right? And those can all be determined based on the appropriate test that's done for the customer. And also, again, on the packaging side. So before maybe a die makes it to its package, should it make it to the package, right? Again, as I said, if the yield is low for a given customer, maybe they need to do wafer map of the, maybe they need a wafer map just to identify which one of the dies need to make it to the package for the integration. So that's actually very briefly what I've got on the importance of testing and what I can identify as some of the examples that we need at Smart Photonics. And I think with that, I'll pass the floor to Anna and any questions that there may be.
Thank you very much, Nazanin. It's great to have the views of the foundries, and I was also very excited that you shared the cost breakdown. Still, testing is expensive, and we need to find ways to reduce it. I ask a question for everyone. I want you to have the first go at this question. At the end of the day, we get the wafer, and we want to test. We want to do the wafer level test. If I do the reverse engineering, if I want to start from the end, how long is it acceptable for a foundry to have the wafer level test being performed at the wafer level test machine? Is it overnight? Is it for a few days? I remember in a meeting we had with IHP, Lars Zimmerman told us, I put the wafer testing at night when I leave, and when I come back in the morning, I want it fully tested. What is the vision of Smart Photonics for your 3 inches wafers?
Ideally overnight. Yeah, absolutely. Ideally, overnight would be the best case scenario because for customers, time is money. So we want fast testing and cheap testing.
Let's make a quick round on that because overnight is slow for me, but I want to see the vision of the others as well. Photonics 42, Antonello Vanocci, one of the people that we have in the packaging of EPIC for the testing. What do you think? What is your idea of the amount of time that a wafer could be tested on a wafer testing machine? I have you muted. I cannot hear you. I think we have a problem with your sound.
Okay.
Yes,
so,
Christo.
okay.
Yeah, perfect.
Okay. So it's mainly depending on what kind of devices you have to test. First of all, you can have a simple device like VCSEL or a more complex device like PIC. If you look at typical numbers for VCSEL, you have in 6-inch wafer around 70,000 VCSELs and more, like 100,000. And for each VCSEL, the time that is dedicated for a full characterization is about 1 second. So this is a figure how critical is the implementation of the probe head from one side and what is all the software.
But Antonello, the numbers don't add up because I have very quick math. So I have 70,000 to 3 seconds per one.
No,
so
1
that's 3
second,
days.
1 second, 1 second, 1 second.
70,000 seconds, that's days, no?
Yeah, so this means that we have to, if you look at full buffer level test, this means that parallel testing is crucial. So this is not, you have not to think about only one channel for time. And then this is one of the bottleneck for to explore a new. And this is a reason why we have to explore a new way of testing procedures and on the same time, what is the best configuration in terms of probe head And this is work that we are doing, sorry, and this is a parallel testing with the multi-probe, multi-site channel is a critical point.
It is $1 million question. I don't expect to have the answer. Another $1 million question is the one that Amir just posted in the chat. For the foundries, Amir, what is your question?
Can you hear me?
Yes.
Jose? Yeah. Thank you very much for the opportunity. Actually, this is sort of a general, question that kind of goes back to this, time question that you asked. So normally, typically, how many components, whether it's waveguides, coupler, MZI modulators, do you normally test before you have the statistics, for the PDK? Is it in the range of hundreds, thousands, tens of thousands, hundreds of thousands? That might actually give us a little bit of an idea.
On my side, I actually don't know the answer, but I can find out and let you know. Obviously, the higher the number of measurements, the better the statistics. So surely we're not looking at tens or hundreds. Hopefully it's a lot more than that, but I'll get back to you about what we actually use.
Thank you.
Thank you very much for this meeting. I think there is, of course, a lot of room to discuss. I can already announce you that we are going to work to set up this working group that Ignazio asked us for his Santa Claus Christmas list. For me, if I had to summarize the learnings of today, the first thing is, of course, we are going there with the fast automation. We saw the presentation from Globalfoundries. We can see how advanced they are. There is still some room to cover on this. The need for multi-probes and parallel testing, combining RF and photonics at very high speed is, of course, coming. Mid-infrared is coming strong, really coming very strong, and we are not ready. Standards. I don't really like the word standards, but I think we need to get more information about the different tests from the foundries, especially when it comes to application dependent. The tendency seems to be to add more complexity on iterative photonics. We saw the presentation on programmable chips from Ghent. Are we ready for that, especially also on the quantum activities? And we really have to address, do we have to test the whole chip or not? And we also have to explore the different advantages of technology. For example, in silicon photonics, we have the vertical grating couplers, and indium phosphide, you have integrated detectors that can be a source for PIC testing. I think at the end of the day, what we have to do is to keep collaborating, to keep working together, because this is really indeed what it's all about. I really want to, first of all, thank everyone for participating at this meeting. It is my job, my life, to continue doing these online meetings. We are going to continue with great meetings from now until Christmas. Please sign up for them. But remember, the meetings are just part of it. The successful is in the collaboration, and for that you need to follow up. When the meeting finishes, Anna and me will relax, we have a coffee, but for you is when the meeting should be starting, because it's all about follow-up. If you want to get in touch with any of the participants, all you have to do is send me an email. I will be more than happy to make the introduction and to make sure that you get in touch with each other on behalf of the dream team of photonics that I'm very happy to be a part of, with people in iterative photonics, in laser, in detectors, in medical. We are here for you. Just please make sure you keep showing up at online meetings and you keep doing the follow-up. Until the next time, from North Pike City, next to the beach, take care of each other and stay healthy and safe. See you soon. Bye-bye.